In this video, we are going to talk about how to determine what's the best order of integration for triple integrals. So let's look at an example. I want to set up a triple integral to find the mass of the solid bounded by z equals 2y, z equals negative y plus 6, and x equals 3 in the first octant, given this formula for the density function in grams per centimeter cubed, where distance in xyz space is measured in centimeters. And by setup here, I just mean to get it in a form where we are ready to apply the fundamental theorem of calculus to evaluate it. So, ordinarily to find mass, I know I need my triple integral over my region of my density function, and then I have my dv, but that is not ready to integrate. So by setup, I don't just mean put it like this. It means actually figure out all the limits of integration and have everything ready to do our antiderivatives. Okay, so here's a graph of this region. But first, let's break down some terminology. So the first octant, kind of like the first quadrant, but for 3 dimensions. It's the part of 3D space where x, y, and z are all positive. So it would be in this portion where x, y, and z are all positive. Okay, and the graphs of these 3 things are all planes. Remember, a plane has the form, like you might have some number times x plus some number times y plus some number times z equaling some constant d on the other side. So these are all in that form. Perhaps some of these coefficients are 0, and that's why not all the variables show up. So z equals 2y is this red plane. Z equals 2y. Z equals negative y plus 6 is the blue one. Z equals negative y plus 6. And x equals 3 is this green one. Some of the quick ways I can tell that are, well, with x equals 3, I notice that every single point here is on 1, 2, 3 on the x-axis. Every single point, no matter how high up we go, has x coordinate 3. For z equals 2y, if I think about my yz plane, I would ordinarily think of this as a line that goes through the origin. It's got a slope of 2, which seems to be reasonable here. But the fact that there's no x in this equation means x could be anything. So any of these points, that x could take on any value. And that makes it span out this way and form a plane and not just a line. Ordinarily, it would also span out this way into the negative x direction. But I don't do that here because it says we are in the first quadrant. And there's a similar explanation we can give for this other equation. It's got a negative slope. I can think of the 6 as, if I continue this line, that would be this z-intercept. Okay, so I'm going to try this in 2 ways. First, let's do it using our dz, dy, dx ordering. That's how we did that last example. So because dz is innermost, I'm going to draw an arrow that's parallel to the z-axis first. And think about, where is that arrow going to enter the region? Where is it going to exit it? So I'll draw a couple arrows. So if I draw my arrow parallel to the z-axis, at some point it's going to hit the bottom of this region. The bottom is on the xy plane. And then it's going to keep going up, and it's going to pierce the surface being this red plane. But if I draw another arrow somewhere else, it's going to hit the bottom somewhere, which I can't really see. And then it'll come out of the top, with the top being this blue plane. So the issue with this is, notice that there's 2 top functions. And because of that, I would need to split this into 2 triple integrals based on, when does it change from this red plane up top to this blue plane? And that change happens where they intersect. So how would I figure out where they intersect? Well, I'd set those equations equal. Set 2y equal to negative y plus 6. Set those z's equal. And if you rearrange this, you'll end up getting that y equals 2. And in fact, if you were to take this line, this orange line, and project it straight down, if you project it straight down onto the xy plane, we'll notice that that projected down line, it's when y equals 1 and then 2. Y equals 2 for every point on that line. That's true up here as well. It's just it's been lifted up and it has higher z values. Okay. So if I think about this base region on the xy plane, this side over here, I'm going to call that base region R1. And this other portion over here, I'm going to call that R2. So if we wanted to do it this way, I would have to split it up into a triple integral over R1 of my density function, plus a triple integral over R2 of that density function. And while we could do that, it's just tedious to have to do two triple integrals. So let's try this another way. Okay, so if I drew a line parallel to the z-axis, the top function, there are two possible values for it. So what if I try drawing an arrow parallel either to the x-axis or to the y-axis? Will the function where we enter and exit, will they ever change? And it turns out for either of those orders, no. So we could do either of them, but let's just pick one for now. Maybe I'll draw an arrow that's parallel to the x-axis. So when I do that, it'll go parallel to the x-axis. It'll hit the back, which I can't really see, and then come out of the front. It'll come out of this green plane on the front. And even if I draw another arrow, it'll hit the back somewhere, and then come out of the front. It'll hit this green plane up at the front. So the back plane is on the YZ plane, that back triangle. And that equation of the YZ plane is x equals 0. And where exits on the green plane, that equation we know is x equals 3. Okay, so if I do this, if I'm drawing an arrow parallel to the x-axis, we are choosing dx as the innermost integral. Then I need to think about, okay, is it going to be dz or dy or the other way around after that? Okay, so, okay, let's think about that. Well, if I go ahead and at least start to set up my triple integral, I know I'll need to have a triple integral at some point. Triple integral, my density function was x plus y plus z. Okay, I know I'm doing the dx innermost, and I'll think about what goes after. Now at least I have these limits of integration for x. Where enters is x equals 0, where exits is x equals 3. Okay. Now for the other ones, the y and the z, we have to draw a shadow of this solid on the YZ plane. So I'm going to project this whole solid onto the YZ plane, And because of the way it looks, this kind of like really nice triangular solid, when I draw it on the YZ plane, it's going to maintain this kind of triangular solid shape. It will have kind of this line coming up and this line going down this way. Okay. We've already figured out the y value of this intersection point, right? We got the y value was 2. The y value there was 2. And if I take the y value and I plug it into either one of these equations, we'll get z. Z is 4. Okay. So now I need to know, well, okay, are we going to deal with dz next? Because then I have to draw a line parallel to the z-axis here. Or am I going to do dy next? Then I got to draw lines parallel to the y-axis. But I notice that if I draw them parallel to the z-axis, the top function changes from this line to that line. So that would make me split it into two triple integrals, which I'm trying to avoid. But if I draw lines parallel to the y-axis, no matter where I draw them, the function on the left stays this line. The function on the right stays this line. So that's going to be most efficient for us. So I'm going to do dy next, because that's the direction of this next arrow, and then that'll force me to do dz last. Okay, so when we do this, dy next and then dz last, now I need to know the equation of each of these curves, the left and the right one, with the y isolated, because y is my next variable. So I got to isolate y in both of these equations. Okay. So if I do that for this first equation, where is it going to enter? So for this first equation where it enters, y equals z over 2. And for this curve where it exits, if I isolate y here, we're going to get that y equals 6 minus z. Okay. So one thing that I want to mention is, while these equations are equations of the whole plane, because of the way that the planes are oriented, when I draw the shadow of this on the YZ plane, that's just going to be the back of this triangle. And the back of this triangle would be dictated by these two equations, but as lines. Okay, that's why I'm just using those same two equations here. All right, so I'm ready for my limits of integration for y. So y goes from, let's see, enters at z over 2 and exits when y equals 6 minus z. Finally, for the outermost variable dz, I just think about the smallest value of z for the region, which is 0, to the biggest, which is 4. And I just use those constants. So z goes from 0 up until 4. And the problem just asked me to set up my triple integral, which means we're done. We have it at this point. Okay, awesome. So just for practice, let's briefly talk about how would we evaluate this. So I've written that out in the notes. So because dx is the innermost thing, I treat x as a variable and y and z as constants. So antiderivative x is x squared over 2. Because y and z are constants, antiderivative y is yx, antiderivative z is zx. I got to plug in x equals 3 and x equals 0 into this. So when I plug in x equals 3, I'll get these three terms. When you plug in x equals 0 into this, you'll get 0, and we got to subtract. And at this point, we just have a double integral, which we've practiced with a bunch. So I'm not going to do all the steps of the double integral, but I'd encourage you to try that for practice. If you do, you'll end up getting 198 for this. So in our next video, we are going to continue practicing how do we recognize which order of integration is best for a triple integral.